Hello and welcome to the fourth of these short talks about mathematical fundamentals, this time logarithms. Start off, what is a logarithm? Well, a logarithm is the inverse function for an exponent. I should explain what I mean by an inverse function. Supposing I have something like y equals x squared. It's a function of x. I put in a value of x and I'll get out a value y. If x was 3, y would be 9. If x was 4, y would be 16, and so on. How do I get from y back to x? That requires a different function. And in the case of x squared, the inverse function is the square root. If y equals x squared, then x equals the square root of y. Now, supposing y was 10 to the power of x, how do I go back from y to get x? And the answer is, that's what a logarithm does. That's the definition of the logarithm function. And I'll write it like that. The 10 indicates that the value of y was taken by doing 10 to the power of x. There are other bases that we use for logarithms as well, notably e and 2, but for now I'll just use the base 10. We can see some examples. If x is 3, then y would be 1,000. Therefore the log to the base 10 of 1,000 must be 3. If x was minus 3, then 10 to the power of minus 3 is 1 over 10 to the power of 3, which is 1 over 1,000. Therefore, log of 1 over 1,000, that's 0.001, is minus 3. 2 is approximately equal to 10 to the power of 0.3. That is such a useful fact that engineers often don't worry about the fact that it's not exactly true, and tend to say that for all practical purposes, 2 is just about equal to 10 to the power of 0.3, and therefore log to the base 10 of 2 is 0.3. It's not exactly true, but it's only wrong by about 1/3 of 1%. Which we often don't worry about. And there's another example here on the slide, which isn't that important, to be honest. I could come up with hundreds of similar examples. Now, why do we use logarithms so much? Well, we often use them in plotting graphs. We plot graphs so that we don't plot, for example, the actual value of x along the x-axis, but we plot the log of the value of x along the x-axis. That would give x here something we called a logarithmic scale. Supposing, for example, we were plotting, let's say, the gain of an amplifier against the frequency. We would usually not plot against the actual frequency, we would plot it against the log of the frequency. So that might be 1, 2, 3, 4, and 5, and so on. Well, if the log is 1, then the frequency is actually 10 to the power of 1, or 10. This is the actual frequency. If the log is 2, the frequency would be 100. If the log is 3, the frequency would be 1,000, which I'll usually write as 1k. If the log is 4, the frequency would be 10,000, which I'll write as 10k. If the log is 5, the frequency would be 100,000, which I'll write as 100k. So these are the actual frequencies that would be plotted at these points on the graph. And you'll notice that they are not spaced uniformly. They're spaced nothing like uniformly. But that's often useful, because it shows us on the graph more about the interesting characteristics of the amplifier. Let me show you an example. Here, I've plotted the gain against the frequency of the same amplifier, first using a linear frequency scale, and secondly on a logarithmic frequency scale. Well, this purple region here is the same group of frequencies as this purple region here. This blue group of frequencies here, from 100 Hz to 1 kHz, you can almost not see it at all on the linear scale, because a linear scale going from 0 Hz to 100 kHz, all of the points between 0 Hz and 1 kHz are in the first 1% of this range. So they're all squeezed into the first 1% of this graph here. Whereas over here, they occupy 1/3 of the available horizontal scale. Here, it is quite clear that at low frequencies, between 100 Hz and 1 kHz, the gain of the amplifier is almost constant. On this graph, you can't see that at all. It's just squashed too much to be visible. And this is one of the main uses of logarithms in electronics. It allows us to plot graphs so that we can see different regions, low frequencies between 100 Hz and 1 kHz, and much bigger ranges of high frequencies, in this case between 10 kHz and 100 kHz, on the same graph clearly. From here to here, there is 90 kHz. From here to here, there is 900 Hz. 1% of the range of frequencies between there and there. But that 1% is often equally interesting to this 90% over here. The other time we come across logarithms is in audio faders like this. You'll see a lot of faders marked like this on mixing desks. We have positive numbers up here, negative numbers down here. That's not so obvious, but these are logarithmically spaced. It says 6, 12, 18, 24, 30. They are actually logarithms. They use something called decibels, which we'll talk about in the next of these little talks. But the difference between 0 and 6 in terms of absolute volume is much greater than the difference between 6 and 12, and that is much greater in terms of absolute volume levels than the difference between 12 and 18, and so on. And this is done because it reflects the way that the human ear works. The human ear has a roughly logarithmic perception of amplitude, of sound volume. So to make something appear half the volume, you have to reduce the amplitude by a lot more than half. I'll be saying quite a bit more about that when we talk about audio circuits later on in the module. Okay, that's all for now. We are now ready to attack something that causes a lot of people a lot of confusion. And that is a rather strange unit called the decibel.